We're back at 2. There's 3 talks from 2 to 3:30, and then there's a reception out here at 3:30. Looking forward on next couple days. So Tuesday for the program at 6 at night, we have a pizza board game night. You're welcome to join if that's your thing. I know it's not everybody's thing, but you're welcome to, come upstairs at 6. Wednesday night, there's a bunch of us that are heading down to Fremont for one of these huge, big haunted houses. You're welcome to join us. It's a bit of a trek, but it's a big production. And then Thursday, we go on a walk up into the hills for about a 75-minute walk. It's it is a little hilly, but it's, I can do it. It's not that challenging. So you're welcome to participate in any of those you like. So our next speaker is Naama, who's the FIDS theorems, tensions between multicore and multinode performance in transactional systems.
Okay, thank you. And thanks everyone for coming. So I'm going to tell you, I guess, about transactional systems. And I'll actually talk about sort of distributed transactional systems and parallel ones. And I'll kind of talk about how they interact. So this was work done with Gal Sela, who is a postdoc at EPFL right now, and Adriana Zegares, who is at Microsoft Research. This was done when all 3 of us were at VMware. Okay, so I'm going to start by talking about transactional systems, sort of introduce the very basic concept in case anyone isn't familiar. So the idea is I have some data system, and there are data items in it. Okay, this is just basically the data in my system. A transaction is basically any piece of code that I get from a user. A user specifies what they want to execute on these data items. So it would be it wants to read some of the data and modify some other data items. Okay, so it gives a read set and a write set of what it wants to access. And I guess we would have several concurrent users at a time. Yes?
Ahead of time. So there's no data dependency.
Good question. We will actually talk about data dependencies, sort of we don't know the read sets ahead of time, read sets, write sets, and they'll build it over time. Okay, so we'll have concurrent users or clients, and each one of them basically will specify what they want to access. And again, in this very simplified sort of example, I'm assuming that I know the data set in advance, and what Phil mentioned is that in many practical cases, you don't actually know the data set. You're just given a piece of code, and depending on the code, if you have some if statements, if I read this, then I will also access this other data item. You kind of build your data set as you're going along in your execution. But for this very simple example, we'll assume that these clients come in and they tell me these are my data items, and they might overlap. And my goal is at a high level, basically, I want each transaction to take effect as if nobody else was in the system at the time. Okay, so I want it to take effect atomically as if it ran in isolation. Okay. All right, so I have sort of a silly example to kind of show why this might get complicated. I might have some university database with data about students, the courses they're enrolled in, and their grades. And maybe I'm the instructor, and I want to look at my database and I want to see, okay, well, if I have a particular course and I look at the student averages of that course and it's too low, then I'm going to bump up the grade of the student with the lowest grade. Okay. At the same time, some student looks at it and says, well, if my average across all my courses is too low, I'm going to drop this very difficult course. And then a third student comes in and says, well, I want to enroll in this course if it has a high average, because I want my life to be easy. So I want to enroll in it, but only if there's room. Okay, so there's sort of 3 transactions going on at the same time, and they're accessing the same data. And they have dependencies, right? So let's say that right now the course's average is too low, but bumping up the student's grade would make it higher than 70. And this student wouldn't drop the course if their grade was bumped up. So there's all sorts of dependencies going on. And if we just kind of let it execute, let's say that we first let the first student read its average, then the instructor will come in, read the course average. The instructor then sees the course average is too low, increases the grade, but oh, too late, the student didn't notice and already dropped the course. Then at this point, the green student would be able to take the course, even though if this sort of inconsistency, where if the pink students would have read their grade correctly, they would never have dropped the course. The green student would never have been able to take the course. So there's sort of some inconsistency that went on here because we allowed the actions to be split. Okay, so this is sort of just an example to show that dependencies kind of make things complicated. Okay, but now let's talk about how transactions are implemented in practice. In reality, this data system is a little bit more complicated. It's made out of just memory locations, right? And we, as the transactional system designer, have to decide how to implement the transactions by accessing these low-level memory locations, right? So we can even decide on how we represent each data item and what it means to access a data item, okay? And our goal is to guarantee serializability, which is basically the correctness guarantee that the transaction either commits atomically, so as if no one else conflicted with it, or it can abort. Okay, it can as the transactional system, I can decide to say, well, I'm aborting your transaction because there were too many conflicts, so your transaction did not take place at all. Okay, so I can either commit, in which case it looks like I committed atomically in isolation, nobody else interfered, or I can abort, and in which case the transaction has to have had no effect whatsoever. Okay, so that's intuitively the condition that's called serializability, and that's sort of the gold standard that we are going to aim for. Okay. Now I want to talk about distributed transactional systems, right? So I kind of presented a transactional system as sort of this one entity in one machine that has data, and we want to implement this concurrency control around it. Right, so this is sort of a very nice abstraction, but in reality, we might have data that is split across several machines. And these machines are connected over a network, right? And at this point, I want to implement my transactions over this distributed system, right? So my data is kind of split across these locations, and a transaction might access data that is located in several different machines. Okay. There's a lot of reasons to go to this distributed setting. First is to physically have more space to store your data. Second is to split the workload. If there's just many, many clients, it's possible that a single machine isn't able to handle all of that workload. So if we split that workload, it might make each machine's life easier. And we also might want to tolerate failures. So if a single machine crashes, we would like to still be able to respond to client requests and make the transactions happen. And so we might distribute just to be able to tolerate machine failures. Okay, and traditionally, the performance bottleneck, the minute you go to the distributed setting, just like was mentioned in the previous talk, the network is sort of your bottleneck, right? Once you communicate across the network, that's where the time goes. That's where everything, sort of all your expense is there. And so your goal is to execute these transactions in as few network round trips as possible. Okay, that's the traditional model. But nowadays, what is starting to happen is that the networks are so fast and they have such high bandwidth that it's starting to be the case that we can actually bottleneck on in-node processing. Okay, so if you don't think about how you'll parallelize inside the node at all, and you kind of just do it on a single sequential CPU, then you can run into bottlenecks where the machine is processing the data too slowly because the network bandwidth is so high. Okay. So now we have to talk about how do we ensure that there is parallel processing within each node, as well as keeping the number of network round trips low. Okay, so now this is the setting we call the parallel distributed transactional system. Okay, we want parallelism within each node, and we also want to distribute our data. Okay. All right. So now the key question that arises is, in this distributed setting, how do we make use of the parallelism in each node as best as possible? Okay, and so let's define our model to kind of make it a little bit more concrete. We have our data set D that's distributed across several nodes. We have n nodes, and inside each node we have m processes. All right. Now each node has some subset of the data set. It's also okay to have the entire data set, in which case we might replicate, so it's possible that each node has the entire data and we just have copies of it, but we also want to talk about the case where each node has just a strict subset of the data. And the nodes are able to send each other messages, but an adversary controls when the messages arrive, so it controls sort of the speed at which the messages go across the network. We're in an asynchronous network, and the adversary also chooses on each machine when a message arrives, which process receives it. Okay, and so this basically kind of models the idea that we don't know which process will be free to sort of read the network buffer and process the next message. Okay, and inside each node, processes communicate over shared memory. So we have this sort of hybrid distributed and shared memory setting. Okay, so a few sort of basic parallelism concepts. A write to a memory location L on a single machine cannot be parallel with any other access to that memory location. Okay, and this is because of cache coherence, right? So in cache coherent systems, sort of once you access a memory location for a write, then you basically you have it in exclusive mode. That means that nobody else is accessing it. Okay, so if we want to expand parallelism, we need to limit the number of writes that happen at the same time as any other person wanting to access the data. Right. Okay, so basically to improve parallelism, we have to limit access to the same location. That's sort of basics of shared memory. Okay. Any questions so far? Good. Okay. All right, so let's define our problem. We have these transactions. We don't know what the transactions will be. They're quite sort of arriving in an online manner. Each transaction is composed of a partially revealed data set. So when we receive it, this is answering Phil's question, we might know some of the data set that it needs to access, but the rest of it might be revealed over time as we're executing the transaction. Okay. And we execute the transaction, sort of, we think of it at the granularity of shared memory steps, but the steps can also include, now I'm going to send a message to another node. Okay. Okay, yeah, and as I said, the more of the data is revealed over time. And we want serializability, right? So the transaction can either appear to execute in isolation or it can abort, in which case it doesn't have any effect. All right. And our goal is to maximize parallelism with these transactions. Okay. All right. Now, the lucky thing is that transactional systems in a parallel setting have been studied a lot. There's an entire literature about how to build efficient parallel transactional systems. Okay, so if we focus on a single machine, there are a few properties that we know have been proven time and time again that they increase parallelism. Okay, so let's focus on sort of two very well-known major properties. One is called the disjoint access parallelism. The intuition behind it is very simple, right? If you have two transactions and their data sets, so the high-level like data that they want to access, if those data sets don't overlap, then the actual low-level memory accesses also should not overlap. Okay, and this is to avoid contention, right? Intuitively, you shouldn't have a lot of like sort of global locations that everyone is accessing and contending on, in order to allow for more parallelism for transactions that inherently don't need to conflict. Yes?
Are you distinguishing read-only from read-write?
Yes, good question, and yes, we do. So in the actual formal definition paper, we actually say if your write set doesn't overlap with another transaction's data set at all, then you shouldn't conflict. Yeah. So in the paper, yes, we distinguish those. All right. And the other very common property that is known to improve parallelism in transactional systems is called invisible reads. Intuitively, that basically means that when you read data items, you shouldn't be making memory, like low-level memory changes. Okay, so basically, if you have two transactions, they have the same write set, but one of them has a bigger read set. The one with a bigger read set shouldn't be making more modifications to the memory. Okay, so that's what invisible reads mean. Any questions about these properties? Okay. And does the intuition of why they sort of increase parallelism, is that clear? It sort of all boils down to the contention and the cache coherence. Okay. So these are properties not from our work. This is something that has been defined in many, many papers, used in many papers in parallel transactional systems.
So Naama,
Yes?
it should never write, right?
Yeah, so if you have a read-only transaction, it should never write.
Okay.
Yeah. But this is also sort of extended to if you have some writes, if you have two, like I said, if you have two transactions, they have the same write set, even if it's non-empty, right? But different read sets, they should still do the same writes.
Okay.
Okay. Yeah.
So do you have a metric that captures the fact that it's not fair just to abort everything?
So we'll talk about, so we have a very, very basic sort of avoid trivial solutions kind of progress guarantee. So we call it a progress guarantee, right? You don't want to abort everything because then you won't be making any progress. In this paper, we only consider an extremely weak sort of don't abort if you are the only person executing. There are many progress guarantees that have been considered that are stronger than that. Okay. So now I'll state sort of the main result at an intuitive level, and then I'll go into more details later. So the main result that we show is that there are tensions between these parallel properties that you want to guarantee and distributed performance properties, right? Where distributed performance, we generally focus on how many round trips does it take for communication. And basically what we show in our work is that you can't achieve basically the best of both worlds. You can't achieve all of the best properties that you would like at the same time. Okay. So what we showed is, first of all, we defined these distributed performance properties. We noticed that in a lot of the literature, while there's a lot of work on distributed transactional systems, the distributed performance properties of we want it to terminate sort of quickly in few rounds, and we want it to be robust against failures and so on, those were only left sort of at an intuitive level, right? Intuitively, I want to decrease round trips, and therefore this is my algorithm, and then a lot of these transactional systems are implemented and tested and shown that they're efficient, but they don't clearly define what these properties mean. So our first contribution is actually just defining these properties. Then we prove this.
Asynchronous?
What?
Is the system asynchronous?
Yes, it's asynchronous. Yeah. Then we prove this impossibility, basically showing that you can't achieve these parallel performance properties as well as the distributed performance properties in the same system at the same time. And we also show that this impossibility result that we have is intuitively tight in some sense, because if you drop any single one of the properties, then you can implement a system that, that satisfies the rest. Okay, so I'll define just one of the distributed performance properties. In the paper, we have another two, actually. I'll just define one in order to get to the first FIDS impossibility theorem statement, and I'll leave it at that for now for this talk. Okay, so remember we were in this image earlier, we had our distributed system. We said that in such distributed transactional systems, really if we focus on the network bottleneck, the place we want to optimize is the number of round trips it takes to commit. Okay, so we're going to formalize this. Okay, what do we want? We want what we call fast decision property. Okay, what does that mean intuitively? We want that if everything works out, if there's not too many conflicts, not too much asynchrony or failures, we want the transaction to commit as fast as possible. Okay, the question is, what does as fast as possible actually mean? Okay, The problem here is that transactions will need different amount of times to actually find out what their data set is. And you can't finish the transaction before it even discovered what its data set is, right? And depending on the transaction, it might need more or fewer rounds to do that. So what we do is, I guess I have an example here of just a transaction that needs more than one round trip to sort of access its data. Okay, so very simple example. Our data set is, we have some global participant pointer that points to either A, B, or C, okay, to tell us who is the current participant in our system right now. Okay, and my transaction says, well, read who is the participant, and if that participant is not null, if there's someone participating in the system right now, then say hello to them. Okay, that's my transaction. Okay, so this transaction, if the participant is not null, then its data set is the participant as well as whoever that participant was, right? Otherwise, if it reads the participant pointer and it discovers that it's null, then that is it. That's all its data set, right? So in some executions, its data set will be just reading the participant. And in other executions, the read set will be the participant and the write set will be whoever the participant pointed at. Okay, so this is sort of a very simple example of how you can have a transaction that doesn't know its data set ahead of time. Okay, and let's say that these boxes show us this sits on node number 1 and this sits on another machine, node number 2. Okay, so they sit on different nodes. That means that I definitely need at least one round trip to even discover whether I need to access the other machine, right? And in my second round trip, I can access both of the machines at the same time. I can tell machine number 2, hey, I want to write this. And I can also tell machine number 1, okay, we're going to commit the transaction, right? Because the machines also need to know that whether the transaction will be committed, right? So in the first round trip, though, I only know one piece of my data set. I don't know the other piece. So I definitely need 2 round trips to even do anything. Okay, okay. So the way we define the fast decision property is basically we say in good executions, right? It's synchronous, it's failure-free, there's no conflicts, everything works out well. What do we need? We want the transaction to terminate within one network round trip after someone knows what the data set is. Okay, so there's many processes in the system. It's possible that some of the processes will discover the data set before the others, right? Maybe one process discovered what the data set is because it read something, and now it needs to notify the others. It needs to send out a message saying, well, I know, right? I've read this, I've gotten to the end of the if statement codes, and I now know that this is the data set, okay? But now what we're gonna do is we're gonna count from the point that a single process knows what the data set is. And from that point, you have a single round trip, network round trip, to communicate with the rest of the machines, let them know what changes need to happen, and the fact that whether the transaction will commit or abort. In this case, it should always commit because we have no conflict. Yeah.
The word knows over here, is this?
This is
How exactly
yeah.
is
So this is the
like,
formal
this is
definition of knowledge. There's been a lot of
I see, so
work
it's like
in.
epistemic knowledge.
This
like
is knowledge. Yeah.
Moses.
This is
I see.
knowledge as is defined by many works in the concurrency setting, right?
I see. So it's not that it actually necessarily has in its memory the locations that are part of its data set or something. It's just that in any possible run from here, that will be the set.
Yeah. That process. Yeah. Basically, for that process, any possible continuation has the same. Yeah. Okay. So a single process has the knowledge. Okay.
So
Yes.
just to follow up on that, so if what I'm doing is some reduction operation on pointers, go from like machine A to machine B to machine D, C, machine D, and I don't know, stop at null or something, I don't need all those memory locations to ever be on one process, right? I just need that last, the one
Right.
that discovers the null.
Right, the one that discovers the
So
null
since
says,
null
"Oh,
is-
okay. Well, I know that we've now collectively discovered."
You know,
Right.
it's the process that Yeah,
Yeah.
so it
So-
never actually saw the data.
Right, it never
So-
actually saw all the data.
Distribution.
Yeah, it never actually saw the data. What it knows is that we have, from this point on, there's no question of what the data set will be, right? And that process, there will be one process that realizes this first, right? And then, yeah, okay. Okay, so that's our definition. Basically, we just had to get over the fact that transactions will need different amounts of time, so we allow that time. We say, take your time, figure out what your data set is. Once you do, though, you have to terminate quickly. Okay. So now I can state our main result. We show this FIDS theorem, which is sort of a theorem of like, if you want all of these properties, you can't achieve all these properties simultaneously. Okay, so our theorem says no sharded system. So sharded means that there's at least one node that doesn't have the entire data set. Okay, so my data isn't just copied in its entirety on all the nodes. Okay, so no sharded system guarantees some non-trivial weak progress that just says you don't always abort all the time. Okay, and these 4 properties. Okay, so it's the fast decision that we just talked about. The 2 properties, invisible reads and disjoint access parallelism, which are very well-known parallelism properties from the parallel transactional system literature, and serializability, which is our correctness condition. Okay. Yeah.
So it's a negative result. The serializability, is it showing the impossibility of serializability sort of in the sense of linearizability, where the appearance of atomicity needs to be within the interval?
It doesn't need to be within.
It doesn't need to be within the interval.
Yeah.
I see.
That would
And
be
even then
strict
it's
serializability.
impossible.
Even then, it's impossible. Yeah. Okay. So I'm going to give you sort of a one-slide intuition for what the proof looks like, and then I'll finish up because I think I'm running a little bit long. Okay. So one-slide intuition of what the proof looks like. Okay. Our general goal in proving such impossibility results is to build an execution where I have conflicting transactions, so they can't be allowed to both commit, but they're sort of unaware of each other, so they are going to both commit, in which case our serializability is broken. Okay, so that's our goal. We're going to find 2 transactions that shouldn't be allowed to both commit, but they do. Okay. All right, and to do that, what we're going to do is we're going to choose 2 very simple transactions that are both going to have potentially empty write sets. They'll only write if in their first read something good happens. Okay, so these are my 2 transactions, and I have 2 data items in my data set in general, sitting on 2 different nodes. And transaction number 1 says I'll read X. If I see the initial value, then I'll write something on Y. And the other transaction does the opposite. It reads Y, and if it sees the initial value, then it'll write something on X. Okay. All right, so they can't both be allowed to commit. It shouldn't be the case that we can get to the situation where so X and Y have both been modified, right? It should be the case that only one of them gets to be modified. What we're going to show is that we can get to such a situation in a system that guarantees all these properties. Okay, and how will we do that? Well, we'll start by arguing that by invisible reads, these transactions can't make any modifications before they discover that they have a non-empty write set, right? And once they discover that, they've actually also discovered their entire data set, in which case they have now a single round trip before they must terminate. Okay, so we basically argue that however they discover their data set, they're not allowed to write anything because of invisible reads before they do discover this data set. And once they do, we now have a single round trip to argue about. We need to argue that during this round trip, they still don't see each other. Okay. And for that, we use disjoint access parallelism. We basically say, well, the property gives us, again, and this goes back to the point that was made before, which is that if we have disjoint access parallelism that takes into account whether it's a read or a write. Okay? So if your write set doesn't overlap with some other transactions data set, then you're not allowed to write to conflict, basically. You're not allowed to write anywhere that the other transaction would see, right? And so on each of so for T1, its write set on X doesn't overlap with T2's data set because it doesn't write on X at all, okay? And so basically we can argue that even in that last round trip, it's not allowed to write on X because of disjoint access parallelism. Okay, so basically we can build this execution arguing using invisible reads and disjoint access parallelism that they won't be able to see each other. Okay. All right, so that's the intuition, and I'll just take a couple minutes to discuss sort of what the implications of this result are. So intuitively what we showed is that this network communication and in-node parallelism are somewhat at odds with each other, right? You can't achieve sort of everything that you would want, sort of your hopes and dreams cannot be achieved simultaneously in a transactional system that is distributed, and you want good parallelism, right? But that's not, we shouldn't lose all hope, right? We can still sort of get something, right? So we can't completely optimize both parallelism and communication, but we could still do a lot, right? We're just saying you can't achieve these specific properties simultaneously. All right, right. So we've shown this tension in our paper. We actually show another theorem that says if you're not sharded, but you do want good failure tolerance, so you have some fault tolerance that is pretty robust. Even if you're not sharded, you can't achieve a system that gives you all of these properties. And we also show that if you drop each one of these properties, then you can build such a system. However, so the algorithms that we showed were sort of proof of concept-y, just showing that you won't be able to strengthen the impossibility results. But the algorithms that we showed were quite inefficient. And in particular, they kind of force aborts as much as possible, right? That makes the algorithm very easy to show that it's correct, but very inefficient. And we haven't actually talked at all about, well, what is the minimum abort rate that you can achieve, right? How can you make such algorithms practical? Even if you do decide on one property to drop, you might end up with a good practical algorithm, and that algorithm is not the one that we had in the paper. Okay, and in general, there's a question of, well, can you achieve high parallelism without invisible reads or disjoint access parallelism? Or can you tweak those properties to make them a little bit weaker, but sort of still not conflict in this manner with the distributed properties and still have something pretty good, right? And also, we didn't talk at all about what happens if we strengthen the progress guarantee, right? So our progress guarantee just said, well, if you're executing alone in the system, you're not allowed to abort, right? That was our property that just prevented trivial abort everything solutions, right? But we didn't look at all into, well, what if we want to guarantee stronger properties, which kind of relates to the minimizing abort rate, but kind of formalizing it a bit more. Right? And we have no answers on that. We just had sort of, there is some tension between these properties. We do have to think a bit deeper when we go from just single node or sort of just distributed to some system that cares about both our parallelism and our distributed properties. So that's it. Thanks.
Questions?
How brittle is the one round trip thing? Like if I said 2 round trips, can I just expand my example to?
Yes, if you do 2 round trips, then the impossibility doesn't hold.
Does not hold?
Yeah. 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 But sort of the round trips intuitively, they do cost a lot, right? They just, the latency is fairly high compared to everything else. So we wanted, the single round trip you cannot achieve. If you give 2 round trips, then our possibility doesn't hold. Yeah. Mm-hmm.
Do you know what people do in practice? Like, are there examples of distributed parallel transaction processing systems out there, and what do they sacrifice?
Yeah, that's a good question. There is a transactional system that sacrifices invisible reads, And I know because Adriana, who is a co-author on this paper, was also a co-author on that paper. She said that they worked really hard to try to achieve invisible reads and they just couldn't. And so that's sort of how we got into this problem. But yeah, they sacrificed invisible reads. Their system is pretty good. And I think it will depend on sort of your workload and the transactions you expect to see and so on to decide like which property to drop. But invisible reads seems to be a pretty popular decision to drop. Yeah.
I guess invisible reads is an example of a property where it talks about the low-level system behavior as opposed to just high-level.
Yeah, so is the disjoint access
Is it possible to
parallelism.
restate the theorem in which, in a way that all of the properties are stated only at the high level without talking about implementation?
So I think if you only state them at the high level, then you're not really talking about the shared memory parallelism, right? Sort of talking about the interaction between the high level and the low level is the parallelism.
I see. You're saying that you're maybe forced to do this.
Yeah, you're sort of forced to
Interesting if
talk
you
about,
were
well,
asked to.
what does my shared memory implementation actually do in order to discuss, well, do I have high contention or not, and how parallel is it? So
I see.
I think it's sort of inherent to the discussion to have some, you have to talk about the low level stuff. Yeah. Yeah.
All right, thanks, Naama.